Welcome to the video on z-scores. We'll start this video by talking about the meaning of a z-score, and then we'll go into some examples of calculating z-scores. First, I need to say that unlike the values we've been talking about in the last couple of weeks, a z-score isn't a value that describes an entire sample or an entire population. Instead, a z-score is a value that describes one specific individual. A z-score is a value that's calculated to show how extreme a certain individual is compared to other individuals. More specifically, a z-score shows how far below average or how far above average an individual is. If I asked you what type of a value could I calculate to show how far below average or above average a certain individual is, you would probably tell me to calculate a deviation. You would probably tell me to subtract the data value by the mean, and then I'll get a deviation that shows how far below average or above average the data value is. It's true that a deviation does show how far below average or above average a certain individual is. For example, if a person's deviation comes out to -5, then the person is 5 below the mean. If the person's deviation comes out to +5, the person is 5 above the mean. The only problem with using a deviation to show how far below or above average a certain individual is that deviations can only be used to compare people who are inside the same population. There's nothing wrong with calculating a deviation to show how far below the mean or above the mean a certain individual is. However, if you're in a situation in which you've recorded the data values of two people, and you want to decide which of the two people has the more extreme data value, then the deviations of the two people are only useful if the two people came from the same population. I'll spend some time explaining what I mean by that. Let's imagine that you're in a situation in which you recorded the data values of two people, and you want to decide which person has the more extreme data value. If the two people came from the same population, then the deviations of the two people would tell you which person is more extreme. When two people are members of the same population, deciding which person is more extreme is actually pretty simple. The person with the smaller deviation is less extreme because that person is closer to the mean of the population, and the person with the larger deviation is more extreme because that person is further away from the mean of the population. Here's an example. If the mean exam score of a certain class is 75, a student in that class with an exam score of 80 has a deviation of +5, because that student is 5 above the mean. And a student in the class with an exam score of 85 has a deviation of +10, because that student is 10 above the mean of the class. The student with the exam score of 85 and the deviation of +10 is more extreme, because that student's exam score is further from the mean of the class. Unfortunately, when two people come from different populations, deciding which person is more extreme isn't so simple. When two people are members of different populations, the deviations of the two people won't tell you which person is more extreme. I think that point will make more sense after I share an example. Let's pretend that two different classes have both taken the same exam. Both classes have a mean exam score of 75. In the first class, almost all of the students are in the 70s. In other words, in the first class, almost all of the students have exam scores that are pretty close to the mean. In the first class, the exam scores have pretty low dispersion. However, in the second class, the students' exam scores are spread out across a much wider range. In the second class, the exam scores have much more dispersion. In the second class, there are several students in the 50s, 60s, 70s, 80s, and 90s. If you think about it, a student in the first class who has an exam score of 80 is actually pretty extreme. In the first class, almost everyone is in the 70s, so a student with an exam score of 80 is at the top of the class. It's true that this student is only 5 above the mean, with a deviation of +5, but the student is pretty extreme because he or she is further away from the mean than most of the other students in the class. Also, if you think about it, a student in the second class who has an exam score of 85 actually isn't very extreme. It's true that that student is 10 above the mean, with a deviation of +10, but that student's exam score isn't very extreme, simply because there are quite a few other students in the class who are even further away from the mean than that student. Let's now think about which of those two students has the more extreme exam score. The first student, with the exam score of 80 and the deviation of +5, is actually more extreme than the student with the exam score of 85 and the deviation of +10. That's because the student with the exam score of 80 was at the top of his or her class, while the student with the exam score of 85 had quite a few students above that student in his or her class. Basically, when two people come from different populations, the person who is more extreme isn't necessarily the person who is further away from average. The more extreme person is the person with fewer other population members beyond them. That's why the deviations of the two people don't tell you which person is more extreme when the two people come from different populations. It turns out that there is a value that can be used to decide which of two people is more extreme when the two people come from different populations. That value is called a z-score. Unlike a deviation, a z-score doesn't simply show how far below the mean or above the mean a certain data value is. Instead, a z-score shows the number of standard deviations that a data value falls below or above the mean. If one person has a larger z-score and another person has a smaller z-score, we'll automatically know that the person with the larger z-score is more extreme, even if the two people came from different populations. That's why a z-score is useful. For example, if we calculated the z-score of the student from the first class who had an exam score of 80, and we calculated the z-score of the student from the second class who had an exam score of 85, the student with the exam score of 80 would actually have a larger z-score because in the population that that student came from, that student was actually pretty extreme. That student was at the top of his or her class. So, overall, a z-score measures how far a certain data value falls below or above the mean. And more specifically, a z-score shows the number of standard deviations that a certain data value falls below or above the mean. In a certain group of people, a person who is right at the mean of the group will have a z-score of 0. For example, if a certain class takes an exam and the mean exam score of the class is 75, then a student in the class who has an exam score of 75 will have a z-score of 0. That student would have a z-score of 0 because that student's exam score was right at the mean of 75. A person who is one standard deviation above the mean has a z-score of +1. So a student in the class who has an exam score that's one standard deviation above the mean would have a z-score of +1. A person who falls one standard deviation below the mean has a z-score of -1. A person who falls 2 standard deviations above the mean has a z-score of +2. A person who falls 2 standard deviations below the mean has a z-score of -2. And you could probably guess that a person who falls 3 standard deviations above the mean has a z-score of +3, and a person who falls 3 standard deviations below the mean has a z-score of -3. So overall, a person who's right at the mean has a z-score of 0. A person who's above the mean has a positive z-score, and a person who's below the mean has a negative z-score. Also, the further a person falls above the mean, the further above 0 that person's z-score will be, and the further a person falls below the mean, the further below 0 that person's z-score will be. For example, a person with a z-score of +2 is further above the mean than a person with a z-score of +1, and a person with a z-score of -2 is further below the mean than a person with a z-score of -1. Here we can see that a person who falls right at the mean has a z-score of 0. A person who's one standard deviation above the mean has a z-score of +1. A person who's 1 standard deviation below the mean has a z-score of -1. A person who's 2 standard deviations above the mean has a z-score of +2. And a person out here who's 2 standard deviations below the mean has a z-score of -2. Let's now think about a population that has a standard deviation of 5. For example, maybe a certain class takes an exam and the standard deviation of their exam scores turns out to be 5. If that's true, then a student in the class who has an exam score right at the mean would have a z-score of 0, like always. A student with an exam score that's 5 above the mean would have a z-score of +1, because that student would be 1 standard deviation above the mean. If the standard deviation of the class is 5, then a person who is 5 above the mean is 1 standard deviation above the mean. So that person has a z-score of +1. A student in the class with an exam score that's 5 below the mean would have a z-score of -1, because that student would be 1 standard deviation below the mean. If the standard deviation of the class is 5, then a student who is 5 below the mean is 1 standard deviation below the mean. A student in the class who has an exam score that's 10 above the mean would have a z-score of +2, because if the standard deviation of the class is 5, then a person who is 10 above the mean is 2 standard deviations above the mean. If you start at the mean of the class and you go up by 5, and then you go up by 5 again, then you've gone up by 2 standard deviations of 5, and you've reached a student who's 10 above the mean. A student in the class who's 10 below the mean would be 2 standard deviations of 5 below the mean, so that student would have a z-score of -2. If you start at the mean of the class, and you go down by 5, and you go down by 5 again, you've gone 2 standard deviations below the mean, and you've reached a student who's 10 below the mean, and that student has a z-score of -2. That student has a z-score of -2 because that student is 2 standard deviations below the mean. A student who's 15 above the mean would have a z-score of +3 because that student would be 3 standard deviations above the mean. If you start at the mean of the class and you go up by 5, you go up by 5, and you go up by 5 again, then you've reached this student right here, who's 3 standard deviations above the mean. A student in the class who has an exam score that's 15 below the mean would have a z-score of -3 because this student is 3 standard deviations below the mean. If you start at the mean and you go down by 5, you go down by 5 again, and you go down by 5 one more time, then you've gone 3 standard deviations below the mean, and you've reached this student right here, who's 15 below the mean, with a z-score of -3. Now what if the standard deviation of the class wasn't 5? What if the standard deviation of the class was 10? Well, in that case, a person in the class who's 10 above the mean would be 1 standard deviation above the mean, and that student would have a z-score of +1. And a student in the class who's 10 below the mean would be 1 standard deviation below the mean, and that student would have a z-score of -1. For example, if the mean of the class was 70, then a student who's right at 70 would have a z-score of 0 because a student who's right at the mean always has a z-score of 0. A person in the class with an exam score of 80, which is 10 above the mean, would have a z-score of +1. And a student in the class with an exam score of 60, which is 10 below the mean, would have a z-score of -1. Now, if the class has a standard deviation of 10, then a student who's 20 above the mean would be 2 standard deviations above the mean, and that student would have a z-score of +2. Because if you start at the mean and you go up by 10, and you go up by 10 again, you've gone up by 20. Also, a student in the class with an exam score 20 below the mean would have a z-score of -2, because if you start at the mean and go down by 10 and go down by 10 again, you've gone 20 below the mean. Also, a person who's 30 above the mean would be 3 standard deviations above the mean, and this student would have a z-score of +3, and a student who's 30 below the mean would be 3 standard deviations below the mean, so they would have a z-score of -3. So basically, the z-score is just a multiple of the standard deviation. In other words, if you go up by 1 standard deviation above the mean, you reach a person with a z-score of +1. If you go up by 1 more standard deviation, you reach a person with a z-score of +2. And if you go up by 1 more standard deviation, you reach a person with a z-score of +3. If you start at the mean and you go down by 1 standard deviation, you reach a person with a z-score of -1. If you go down by 1 more standard deviation, you reach a person with a z-score of -2. And if you go down by even 1 more standard deviation, you reach a person with a z-score of -3. Let's now go through an example in which we take the data values of 5 people and we turn each data value into a z-score. We're imagining that these 5 people come from a population in which the mean height is 60 inches and the standard deviation is 5 inches. Let's start by finding the z-score of person 1. Person 1 is 50 inches tall, so person 1 is 10 inches below the mean of 60. In order to find out the z-score of person 1, we have to find out how many standard deviations person 1 falls below the mean. To do that, we can start at the height of 60 and go down by 5s until we reach this height of 50. So if you start at 60 and you go down by 5, that's 55. And if you go down by 5 again, that's 50. So we started at 60 and we went down by 2 standard deviations and then we reached 50. So this person right here is 2 standard deviations below the mean. So this person has a z-score of -2. This person 2, who has a height of 55 inches, is 5 inches below the mean of 60. To find this person's z-score, we need to start at the mean height of 60 and go down by 5s until we reach this height of 55. So if you start at 60 and you go down by 5 one time, you reach 55. So this person is 1 standard deviation below the mean, so this person has a z-score of -1. This person who has a height of 60 inches is right at the mean of 60, so this person has a z-score of 0. This person who has a height of 65 inches is 5 inches above the mean of 60. So to find this person's z-score, we need to start at the mean of 60 and go up by 5s until we reach this person's height of 65. So if you start at 60 and you go up by 5 one time, you get to 65. So this person is 1 standard deviation above the mean, so this person has a z-score of +1. This last person, who's 70 inches tall, is 10 above the mean of 60. To find this person's z-score, we need to start at the mean of 60 and go, and go up by 5s until we reach this height of 70. So if you start at 60 and you go up by 5 and you go up by 5 again, you get to 70. So this person is 2 standard deviations above the mean of 60. So this person has a z-score of +2. So we've just found out that these 5 people have z-scores of -2, -2, -1, 0, +1, and +2. And here I've made a diagram of what we just did. I said that the person who's right at the mean of 60 has a z-score of 0. The person who's at 55 is 1 standard deviation of 5 below the mean. So this person has a z-score of -1. This person who's 50 inches tall is 2 standard deviations of 5 below the mean of 60. So this person has a z-score of -2. This person who's 65 inches tall is 1 standard deviation of 5 above the mean. So this person has a z-score of +1. And this person who's 70 inches tall is 2 standard deviations of 5 above the mean of 60. Which means that this person right here has a z-score of +2. So I hope this diagram makes it clear that since the standard deviation is 5, that the z-score is really just showing a multiple of 5. This person who has a z-score of +1 is just 5 above the mean. This person who has a z-score of +2 is just 2 5s above the mean. Now let's look at another example right here. The standard deviation of the population is still 5 inches, so we're still dealing with 5s. But this time we have some different numbers than we had before. Well, we know that if the mean is 60 and the standard deviation is 5, that a person with a height of 50 is 2 standard deviations below the mean, so they have a z-score of -2. And each person who's right at the mean of 60 has a z-score of 0. And the person who has a height of 70 is 2 standard deviations above the mean, so they have a z-score of +2. So now let's look at these people on a diagram. These 3 people are right at the mean of 60, so they all have a z-score of 0. We don't have anyone who's 1 standard deviation above the mean right here, so we don't have anyone who has a z-score of +1 in this example. But we do have someone who's 2 standard deviations above the mean with a z-score of +2. We don't have anyone who's 1 standard deviation below the mean, so no one has a z-score of -1 in these 5 people. But we do have someone who's 2 standard deviations below the mean down here. So this person has a z-score of -2. Once again, I hope these bars down here make it clear that the z-score is just the number of standard deviations that a person falls below or above the mean. Let's now go through an example in which the standard deviation is no longer 5. Now we're imagining that these 5 people come from a population that has a mean height of 60 inches and a standard deviation of 10 inches. So the mean of the population has stayed the same, but the standard deviation has gone up. So the population has a little bit more dispersion than it did before. If the standard deviation of the population is 10, then this person who has a height of 40 is 2 standard deviations below the mean, because if you start at 60 and you go down by 10, that's 50, and if you go down by 10 a second time, that's 40. So this person has a z-score of -2. This person who has a height of 50 inches is 1 standard deviation below the mean, because if you start at 60 and go down by 10 one time, that's 50. So this person has a z-score of -1. This person who has a height of 60 inches is right at the mean, so this person has a z-score of 0. This person who's 70 inches tall is 1 standard deviation above the mean, because if you start at the mean of 60 and go up by 10 one time, you get to 70. So this person who's 70 inches tall has a z-score of +1. This person who's 80 inches tall is 2 standard deviations above the mean, because if you start at the mean of 60 and go up by 10, and then you go up by 10 a second time, you get to 80. So this person who's 80 inches tall has a z-score of +2. Once again, let's make a diagram to make this a little bit more clear, and so you can have a visual of what's happening. So we can see that if you start at 60, at the mean of 60, and you go up by 1 standard deviation of 10, you get to this person who's at plus 1. If you start at 60 and go down by 1 standard deviation of 10, you get to this person who's at minus 1. If you go up by 10 twice, you get to this person who's at plus 2. And if you go down by 10 twice, you get to this person who's at minus 2. So this is the same diagram that we had last time. The only difference is that the standard deviation has changed from 5 to 10. So now each of our standard deviation bars is 10 instead of 5. Let's now look at an example in which the population mean is still 60 and the standard deviation is still 10, but the 5 heights have changed. Well, we know that this person who's 50 inches tall has a z-score of minus 1 because if you start at 60 and go down by 10, you get to 50. And we know that all of these people who were 60 inches tall have z-scores of 0 because they're right at the mean. And we also know that this person who has a height of 80 inches has a z-score of plus 2 because if you start at 60 and go up by 10, that's 70. And if you go up by 10 a second time, that's 80. Once again, we can look at a visual. So this time we have one person with a z-score of minus 1, 3 people with a z-score of 0, and 1 person with a z-score of plus 2. And I hope these diagrams make it clear that people who are more extreme and are further away from the mean have bigger z-scores, because people who are far above the mean in this direction have z-scores that are big positive numbers, and people who are far below the mean in this direction have z-scores that are big negative numbers. So if we kept on going, if we extended this number line, eventually we would have a tick mark for 100, and that would be plus 4. A person with a z-score of plus 4 would be pretty far above the mean, because they would be 100 inches tall. Also, if we extended the number line in this direction, eventually we would get to a height of 10 inches, which would be a z-score of minus 5. That would be pretty far below the mean. So basically, a person who has a big positive z-score is far above the mean, and a person who has a big negative z-score is far below the mean. So far we've been finding people's z-scores by just starting at the mean and counting upwards by standard deviations, or by starting at the mean and counting downward by standard deviations. And it might have seemed like I was doing it the hard way. You might have been thinking, isn't there a formula that can be used to find a z-score? Well, there is actually a formula that can be used, and the reason why I was doing it the hard way is just to make it clear what a z-score actually stands for. I wanted to make it stand out that a z-score is just the number of standard deviations. But now at this point, I think a z-score is conceptually clear. I think you understand the concept of a z-score, so from now on we'll just use the formula to find z-scores. And this is the formula. The formula for a z-score is just the data value minus the mean divided by the standard deviation. So like I said, we could have used this formula all along to find the z-scores, but I was doing it the hard way to help you understand the concept of a z-score. If you wanted to change this to symbols, x is the symbol for the data value. Mu, the Greek letter mu, is a symbol for the population mean, and the Greek letter sigma is a symbol for the population standard deviation. Now let's go through an example of using the formula to calculate a z-score. So we have a person who's 45 inches tall, and that person is a member of a population that has a mean height of 70 and a standard deviation of 7. So the entire the entire population that this person comes from has a mean of 70 and a standard deviation of 7, and this individual person has a height of 45. And we want to find out this person's z-score. To find this person's z-score, we just subtract the person's data value of 45 by the mean of 70 and divide by the standard deviation of 7. So we can do this in just a few steps. First, we have to subtract on top of the fraction. So 45 minus 70 equals negative 25. Now that we've subtracted on top of the fraction, we just divide by the standard deviation on the bottom. So negative 25 divided by 7 is negative 3.6. So the person's z-score is negative 3.6. So we've subtracted on top first, and then we divided by 7 on the bottom. 45 minus 70 was negative 25, and then negative 25 divided by 7 was negative 3.6. So now we have a person who's 85 inches tall and comes from a population with a mean height of 70 and a standard deviation of 7. We're going to use the same formula to find this person's z-score. And since this person is above the mean, this person's z-score is going to end up being a positive number. So 85 minus 70 equals 10. I'm sorry, 85 minus 70 equals 15. And 15 divided by 7 is 2.1. So this person's z-score is 2.1. So I hope this formula is also making it clear that a z-score doesn't have to be a whole number. It can have a decimal at the end. Now let's go through an example in which we find the z-scores of these three heights. And we're going to use the formula to find each of these z-scores. Let's start with this person who's 50 inches tall. Well, this is telling us that this person comes from a population with a mean height of 60 and a standard deviation of 8. So we're going to subtract the person's height of 50 by the mean of 60 and divide by the standard deviation of 8. 50 minus 60 equals negative 10, and negative 10 divided by 8 is negative 1.5. So this first person has a z-score of negative 1.25. All three of these people are coming from the same population. So this person who's 55 inches tall also comes from this population with a mean height of 60 and standard deviation of 8. So to get this person's z-score, we're going to subtract by the same mean of 60 and divide by the same standard deviation of 8. So 55 minus 60 is negative 5 on top, and negative 5 divided by 8 is negative 0.625. This is the z-score of person 2. So we can see that, so far we can see that since these two people are both below the mean of 60, they both have negative z-scores. Now what about this person right here, who's 60 inches tall? This person is right at the mean of 60, so we already know that that person's z-score is going to be 0, but let's go through the formula just to show that that's true. We take the person's height of 60, subtract it by the mean of 60, and the top comes out to 0. And 0 divided by anything equals 0, so this person's z-score is 0. So these are the z-scores of the three people. We've just taken these three heights and we've changed them to z-scores. So I hope that this makes it clear that each person has both a data value and a z-score that goes along with the data value. The z-score just shows the number of standard deviations that the data value falls below or above the mean. Here's one more example. This example is a little bit different because now we're imagining that these three people make up the entire population. This is a small population of 3 people. So it looks like it's 3 students who are in a class together, and they've all taken an exam. And we want to find the z-scores of these 3 people. And we actually don't know what the mean and standard deviation of the population are. But since we know that these are the only 3 people in the population, we can actually use their data values to calculate the mean and standard deviation of the population. So in this example, we're going to go through a few more steps. We're going to actually calculate the mean and standard deviation of the population, and then calculate the z-score of each of the 3 people. So first, let's find the population mean. To get the population mean, we just add the exam scores of all 3 population members and divide the total by 3, because there's 3 of them, and we get 80. So the mean exam score of this small population is 80. Now we have to find the standard deviation of this small population. Well, to get the standard deviation, we just subtract each data value by the mean of 80 to get the deviations. The deviations are -5, 0, and +5, because this value is 5 below the mean, which means the deviation is -5. This score is at the mean, so it has a deviation of 0, and this score is 5 above the mean, so it has a deviation of +5. Now we have to square each deviation, meaning we have to multiply each deviation by itself. So -5 times -5 is 25. 0 times 0 is 0. 5 times 5 is 25. The next step in finding the standard deviation is to calculate the mean of the squared deviations. So there's 3 squared deviations here. So to get the mean of the squared deviations, we just add them and divide by 3. And we get 16.7. Also remember that when you're calculating the standard deviation of an entire population, like we are here, you don't drop this number down by 1. It just stays at the number of squared deviations. So we don't drop this down to 2. It just stays at 3. And remember that the mean of the squared deviations, which we just found right here, is called the variance. So we have a variance of 16.7, and the standard deviation is the square root of the variance. If you calculate the square root of 16.7 by just hitting the square root key, it's 4.08, or it rounds to 4.1. So this population has a standard deviation of 4.1. Now that we know that this small population of 3 people has a mean of 80 and a standard deviation of 4.1, we now have all the information we need to get the z-score of each person. So what we're going to do is we're going to take each person's exam score, subtract it by the mean of 80, and divide by the standard deviation of 4.1 to get the person's z-score. Let's start with person 1. 75 minus the mean of 80 is -5, and -5 divided by the standard deviation of 4.1 is -1.2, because -5 divided by 4.1 is -1.2. So we know that person 1 has a z-score of -1.2. To get the second person's z-score, we subtract the second person's exam score of 80 by the mean of 80 and divide by the standard deviation. 80 minus 80 is 0, and 0 divided by 4.1 is just 0. So like I said, a person who's right at the mean will always have a z-score of 0. Now we need to find the z-score of person 3, who has the exam score of 85. So 85 minus the mean of 80 on top equals +5. And +5 divided by the standard deviation of 4.1 is 1.2. So now we've just found the z-scores of all three people. And we can make a column right here to show each person's exam score and each person's z-score. We're almost at the end of the video. I just wanted to do a demonstration in which I show you how to calculate z-scores in Excel. And then after that, I'll talk a little bit about how z-scores are useful when a population follows a normal distribution. This is just a list of numbers that I made up and typed into Excel. But let's pretend that these are the exam scores of 20 students who are taking a class together. We're going to change each person's exam score into a z-score. Before we can do that, we have to find out what the mean and standard deviation of the class equals. We can find the mean of the class by clicking on an empty cell down here and typing in equals and then the word average and then putting a left parentheses right here and then highlighting all of the numbers in the column and then closing the parentheses and then pressing enter. So right now it says equals average and then A2 colon A21 in parentheses. What this is saying is that it's going to calculate the average of all numbers from A2 to A21, which is this entire column. So now I'll press enter, and it gives me the mean exam score of the class, which comes out to 77.85. Now I want to get the standard deviation of the class. So I'll click on another empty cell down here, and I'll type in equals STDEV. And then I have to actually type in .p, since it's an entire population. When I type in equals STDEV.p, it calculates this. It tells Excel that I'm calculating the standard deviation of an entire population. So Excel won't use n-1. It'll just use the formula with n. Remember that there's two formulas for a standard deviation, one for a sample and one for a population. Now I type in the left parentheses and I highlight all of the exam scores. I'm not highlighting this number because this wasn't one of the exam scores. This is the mean that we calculated. Now I close the parentheses and I press enter, and it gives me the standard deviation of the class. So down here I have the mean exam score of the class and the standard deviation of the class. Now I can find each student's z-score. I can find each student's z-score by subtracting each exam score by the mean and then dividing by the standard deviation. So I need to highlight this cell right here, and then in this cell I type in equals. In Excel you always have to start with an equal sign when you're calculating something. Then I enter a left parentheses. I highlight this first exam score of 25. I type in a subtraction sign, and then I click on the mean down here, which we calculated together. Then I type in a right parentheses, and then I type in this slash right here. It's a division sign. And then I click on the standard deviation down here. And once I press enter, Excel is going to subtract 25 by the mean, and then divide the answer by the standard deviation. And that'll give us the z-score of person 1 right here. So I press enter. So person 1, who had an exam score of 25, had a z-score of negative 3.33, roughly. So this student's exam score is pretty far below the mean of 77. That's why the z-score is such a big negative number. If I hover the mouse right here at the bottom right, and then I click, I can drag this down, and it'll do the same calculations for every number, or it should. I think what I actually have to do is right here. I have to type in a $sign and a $sign right here, and then also for the standard deviation, I have to type in these $signs, because in Excel, if I use these $signs, it knows to subtract by this number every time, and then divide by this number every time. So I'm going to press enter, and then now if I drag down, it should do the same calculations for every value. So for each of these exam scores, it subtracted it by the mean and divided it by the standard deviation. So these are the exam scores of the 20 students, and these are the z-scores of the 20 students. Each student has both an exam score and a z-score. We can see that the student who's the furthest below the mean has the z-score that's the furthest below 0. We can see that the student who is the furthest above the mean has the z-score that's the furthest above 0. And we can also see that the students who have exam scores that are pretty close to the mean have z-scores that are pretty close to 0. So a z-score shows how far a person is below the mean or above the mean. In other words, a z-score shows how extreme a person's value is compared to the mean. Now that we've done this demonstration in Excel, I'll just make a few more points about how z-scores are useful when a population follows a normal distribution. One important point I wanted to make is that if a population follows a normal distribution, then it's possible to calculate how many people fall below a certain z-score, above a certain z-score, or between two z-scores. And here are some examples that I'll share with you. If a population follows a normal distribution, then 68% of the population has a z-score between -1 and +1. 68% of them fall in here. Only 16% of the population has a z-score below -1, and only 16% of the population has a z-score above 1 out here. Also, if the population is normal, 95% of the population has a z-score between -2 and +2. Only 2.5% of the population are out here below -2, and only 2.5% of the population are out here above +2. And if a population is normal, it turns out that 99.7% of the population has a z-score between -3 and +3, and only 0.15% are out here below -3, and only 0.15% are out here above +3. And these percentages that I just shared with you are actually always correct if the population is normal. It doesn't matter what this standard deviation actually equals. I'll share a real-life example with you. We know that in the general population, IQ scores follow a normal distribution or a bell-shaped curve. We also know that in the general population, the mean IQ score is 100, and the standard deviation of IQ scores is 15. That means that a person who has an IQ score of 100 has a z-score of 0, since that person is right at the mean. It also means that a person who's 15 below 100 at 85 has a z-score of -1, and a person who's 15 above 100 at 115 has a z-score of +1. So 85 is -1, and 115 is +1. Since IQ scores follow a normal distribution, we know that 68% of the population falls between 85 and 115, because, like I said, when a population is normal, 68% of the population fall between -1 and +1. Also, a person with an IQ of 70 would have a z-score of -2, and a person with an IQ of 130 would have a z-score of +2, because if you start at 100 and go down by 15, that's 85. And if you go down by 15 again, that's 70. And if you start at 100 and go up by 15, that's 115. And if you go up by 15 again, that's 130. So a person with an IQ of 70 is at -2, and a person with an IQ of 130 is at +2. Since IQ scores follow a normal distribution in the population, we know that 95% of the population has an IQ between 70 and 130, because like I said, if the population is normal, then 95% of the population falls between the z-scores of -2 and +2. Now let's think about what IQ scores go along with -3 and +3. Well, if you start at 100 and you go down by 15, that's 85. If you go down by 15 again, that's 70. If you go down by 15 one more time, that's 55. So 55 goes along with -3. If you start at 100 and you go up by 15, that's 115. If you go up by 15 again, it's 130. If you go up by 15 again, it's 145. So -3 is an IQ of 55, and 145 goes along with +3. And I told you just now that if a population is normal, 99.7% of the population falls between -3 and +3. That means that in the general population, 99.7% of people have an IQ between 55 and 145.